Dear learners, now we are going to solve next numerical problem, which is 6.4. The statement of 6.4 numerical problem at your textbook is as water is flowing smoothly through a closed pipe system. At one point the speed of water is 3.0 meter per second, while at the another point 3.0 meter higher. The speed is 4 meter per second. If the pressure is 80 kilopascal at the lower point, what is pressure at the upper point? I will repeat the statement. Water is flowing smoothly through a closed pipe system. At one point the speed of water is 3 meter per second, while at another point 3 meter higher the speed is 4 meter per second. If the pressure is 80 kilopascal at the lower end, what is pressure at the upper end? Student, here we have given a situation. There is a closed system of pipe, and through this pipe, top of the end of the pipe is 40. There is yes, at the point of speed is 3 meter per second, while another point which is 3 meter above. The lower end, where the pipe of, like this, we have a pipe. So upper end there is speed of 4 meter per second, and lower end is 3 meter per second, and this portion is from the above the ground. Consider this is ground, is 3 meter, yes, 3 meter higher. Yes, this is 3 meter higher. Consider this is a closed pipe system. We have given there is a closed pipe system, the upper portion having water flow speed 4 meter per second, lower end is 3 meter per second, and the higher the is 3 meters. So students, here we have the given pressure is what is pressure? If the pressure is lower end the pressure is given as 80 kilopascal. Here the pressure is given as 80 kilopascal, and which is the P2, and P1 pressure we will have to find out the P1. So this diagram resembles to the Bernoulli's equation, Bernoulli's principle, which we have learned in our previous lecture of 6th chapter, which is Bernoulli's equation. We have driven out the formula, we have derived the formula of Bernoulli's principle or Bernoulli's equation. So to solve this numerical problem, we will use the Bernoulli's equation, and the given data of this numerical problem is as speed of water at one point, which can be written as V1 3 meter per second, speed of water at another end, another point, which can be written as V2 4 meter per second. Now students, height of the point, height of the upper point can be written as H2 3 meter, and height of the lower point can be written as H1, which is at the ground, and we can write as 0 meter. Now another thing, density of water we can write as, we know density of water, you should have an idea what is the density of water. Rho equal 1000 kilogram per meter cube, which is fixed for water. Pressure at the lower end, at the lower point, can be written as P1, which is given as 80 kilopascal, or P1 can be written as 80 10 raised to power 3 Pascal, or can be written as P1 equal 8030 of kilopascal. And what will we have to find out? We will have to find out to find Yes, dear students, we will have to find out the pressure at the other end, which is upper side pressure, which is at the upper end. P2, we will have to find out the pressure at the upper end, which is P2, which can be written as P2. So students, to solve this numerical problem, we will use the Bernoulli's principle or Bernoulli's equation. P1 plus half rho V1 square plus rho GH1 equal P2 plus half rho V2 square plus rho GH2. As students, H1 is 0, so this term will be 0. Now the remaining terms, P1 plus half rho V1 square equal P2 square plus half rho V2 square plus rho into GH square. Now substituting the values, P1 is given as V1 given as 3 square. P2, we will have to find out the P2, 1 by 2. Here same values, velocity is 4 meter per second square plus rho is 1000 and multiply by 9.8 multiply by H2 is, which is 3 meter. So students, we simply multiply in those quantities. When we will multiply this one 500 and this should be 9. When we solve this, it should be also 500. When we solve this, then we will have as so when we solve this term, then we will have 8,000. Then we will solve this term, we will have 29,400. Then we will have to find out the P2, which is pressure at the upper point. So P2, by rearranging this, we can have, when we add this quantity and when we add these two terms, when we add this quantity, this should be 84500 minus 37400 when we add this quantity. Then P2. Okay students, when we add this quantity, we will have 84500. When we add these two quantities, we will have 37400. When we subtract this, we will have pressure 47,100 Newton per meter square. You can write as 4.71 10 raised to power 3 Newton per meter square is Pascal, and you can write this P2 as 4.71 10 raised to, no, we use a kilopascal because our first pressure is given in kilopascal. Then our answer should be in also kilopascal. So this is the answer your book, which is only 47. Yes, 47. 30123 should be 47. 47.1. 47.1, and you can write precisely as by rounding off, we can have 747 kilopascal. So this is the answer of your numerical problem, and in this way you can solve this numerical problem. Students, our next question, numerical problem of 6th chapter is 6.5. The numerical problem statement at your textbook is as an airplane wing is designed so that when the speed of the air across the top of the wing is 450 meter per second, the speed of the air below the wing is 410 meter per second. What is the pressure difference between the top and the bottom of the wings? Density of air is given as 1.29 kilogram per meter cube. I repeat the statement. An airplane wing is designed so that when the speed of the air crosses the top of the wing is 450 meter per second, the speed of the air below the wing is 410 meter per second. What is the pressure difference between the top and the bottom of the wings? Given the air density as 1.29 kilogram per meter cube. So student, here we will have to find out the pressure difference. There are two speed given. One is top of the wing is 450 meter per second, and the lower of the wing is 410 meter per second, and the given density of the air is 1.29 kilogram per meter cube. Student, to solve this numerical problem, first we will write the given data. Speed on the upper side of the wing. Here we will write speed of air on upper side of wing. You can write this as V1, which is given as 450 meter per second. Now the speed of air on lower side of wing, you can write as V2, which is given as 410 meter per second. What will we have to find out? We will have to find out, dear students, the pressure difference between upper and lower side of the wing. Mean to say, to find, here we will have to find out the pressure difference. You can write as pressure difference as P2 minus P1. Here is the quantity we will have to find out. Pressure difference we have given in data as a speed of an air on upper side of wing is V1. We can mention it as V1, 450 meter per second, and the speed of air on the lower side or the lower side should be lower side. Lower side of the wing is given as 410 meter per second. We can write this as a V2. And what will we have to find out? To find pressure difference between two situations. Now students, we have driven out the formula as in Venturi duct or Venturi relation. In our lecture we have driven out the formula from Venturi duct, the difference of the pressures 1/2 rho into V1 square minus V2 square. So students, we will use this formula, which is a relation from the Venturi relation, which is an application of the Bernoulli's principle, Bernoulli's equation, and now we will use this formula to evaluate the numerical problem. So we can write as P2 minus P1 by substituting the values, and one thing I have missed here is the rho, which is the density of the air, which is given as 1.29 kilogram per meter cube. So this is the density which is specially given in brackets at the end statement of your question. So we can write the values, and we will have 1.29 into V. We can put these in square brackets, then small bracket, 450 square minus 410 square, and close the square bracket. When we solve this, we will have P2 minus P1 equal 1.29 over 2. The square of 450 should be 202500. It is 5, not 6. Minus 168100. Kindly make calculation by yourself. Might be there is a little bit mistake I have calculated, so keep in mind, do yourself from this. Actually, our aim is here is that to find out the correct numerical problem solution, to find out the correct formula to solve this numerical problem. And the next working is up to the students, that they should calculate the valuation or evaluate or evaluations or calculations by themselves. So when we take the difference, three, 4, 4, 0, 0. Now when we will cancel this, this is 17, 200. Now when we multiply this, we will have P2 minus P1 as 22180 Newton per meter square. To convert this Newton per meter square, we will divide this by 1000 to convert into kilopascal or kilonewton per meter square. For this sake, we will divide this term by 1000 and it should be converted into kilopascal. So the answer is 22.180 kilopascal, and rounding off we can have. So this is the answer which is required answer, and the answer at your book is the 47. I think it should be 47. No, it should be 22 kilopascal, and there is a mistake. Actually 22 kilopascal is the correct answer at your book. 6.5. Actually I took a wrong eyebird view on the 6.4, which is 47, which we already have driven out and solved out. So this is 6.5. the answer is 22 kilopascal, which is correct at your book. So in this way we can solve this numerical problem. Okay, dear learners, our next numerical problem or chapter 6 fluid dynamics is 6.6. The numerical statement at your textbook is given as the radius of the aorta is about 1 centimeter and the blood flowing through it has speed of about 30 centimeter per second. Calculate the average speed of the blood in the capillaries using the fact that although each capillary has a diameter of about 8 into 10 raised to power minus 4 centimeter, there are literally millions of them, so that their total cross section is about 2000 centimeters square. I will repeat this statement. The radius of the aorta is about 1 centimeter. The blood flowing through it has a speed of about 30 centimeter per second. Calculate the average speed of the blood in the capillaries using the fact that although the capillaries has a diameter of 8 10 raised to power minus 4 centimeter, there are literally millions of them, so that their total cross section is about 2000 centimeters square. Students, we have given that we have an aorta, and to solve this numerical problem we will write the given data as radius of aorta. We have given the size or radius of aorta as aorta. We can mention this as R1, small r1, which is given as 1 centimeter, and convert this 1 centimeter to 1 meter or meter. This should be 10 to the power minus 100 meter. How can we solve this? Because to convert this centimeter we will divide by 100, and this will convert into 1 by 100, and we know that 100 is 10 to the power minus 2, and this 2 in the denominator, when will come on the numerator, it will become 10 to the power minus 2 meter. Now speed of the inflowing blood. Inflowing blood. So students, speed of the inflowing blood is given as we can write this V1 30 centimeter per second. So although this is given as 30 centimeter per second, but we will have to convert this into meter per second. For this sake, we will divide 30 centimeter per second by 100, then we will have meter per second. So this should be 0. Okay, you can write by similarities or symmetry, you can write this as 30 10 raised to power minus 2 meter per second. To this similarity, 10 raised to power minus 2, and we can write this as a 10 raised to power minus 2. And the next is what is the total cross section area of aorta. Total cross section area. We can write this as A2 2000 centimeter square. We will also convert this centimeter to meter. So meter square. For this sake, we will divide 2000 by 10,000. Then it will become A2 as 0.2 meter square. So students, these are the given data, and the average diameter of capillaries is given as, we can mention it like D2 8 10 raised to the power minus 4 centimeter. We can also convert this into meter. For this sake, we will divide by 100, and this 10 raised to the power minus 2 become 8 into 10 raised to the power minus 6 meter. So these are the given information which is given as. So what will we have to find out? We will have to find out the average speed or blood speed to find. So what we will have to find out? We will have to find out the average speed of blood. Average speed of blood we can write as V2. So students, to solve this numerical problem, we can see that in our given data we have given radius of aorta, which we have mentioned as R1, and the speed of inflowing blood, which is we have mentioned as V1 30 centimeter. We convert this to 13 to the minus 2 meter per second, and the total cross section area, which is given as A2, and we can write this A2 and 2000 centimeter square we have converted into meter. Then we will have 0.2 meter square, and the average diameter of the capillaries, which is given and which can be written as D2 8 to the power minus 4 centimeters, and converting this into meter, we will have 8 into 10 to the power minus 6 meter. What will we have to find out? We will have to find out the average speed of the blood. So student, to solve this numerical, we will use the equation of continuity. A1 V1 equal A2 V2, because this is all about the flowing of fluid. So equation of continuity dealt with the flowing of fluid. So we will use the formula of equation of continuity, which is A1 V1 equal A2 V2. Student, here I'm going to solve this by minimizing or by splitting. We know that this is A1 and this is A2, and A1 we have well known pi R1 square into V1, and this should be also pi R2 square V2. Pi cancel out by pi because this is constant on both sides, and you can also write this as a 0.8. we should not cancel out this because we have given the area A2. Okay, you can also solve this by cancelling the pi by pi. For this sake, we will first find out the radius from the R2, from this area. Okay, because this is a spherical, we consider the radius of aorta or blood flowing through it, consider the blood particles as a sphere, and we will find out the volume and 4/3, and this will be long calculation, and we will not split this A2 into pi R2 square. You just split A1 into pi into R1 square. Now substituting the values, pi should be 3.14. R is given as 10 raised to power minus 2 meter, and V1 is given as 30 10 raised to power minus 2 meter per second, and A2 is 0.2 meter. And what we will have to find? We will have to find V2. Now students, I'm going to erase this because there is a less space on the board to solve this. So to solve this, I hope you have noted down it. Now solve this by rearranging this equation. We can have as V2. Now we will have to find the V2, and you know that this term 0.2 is multiplying by V2, and when we take this term on the other side, this will be the denominator of this numerator. This should be like a 3.14. When we take the square, 10 is power minus 2, it should be 10 is power minus 4, and the 30 10 is to power minus 2 will remain the same, now 0.2. When we calculate, when we multiply the numerator's value and divide by 0.2, then we will have 4.71 10 is to power minus 4 meter per second. Our approximate value is 5 into 10 is to power minus 4. This is the approximate value. So this is the value of the blood stream which is flowing inside the aorta or blood vessel, and the answer is correct because this answer is also mentioned in your book. This is 5 into 10 is, but this is not 6, this is 5. 5 into 10 is to power minus 4 meter per second. This is the blood flowing, average blood flowing or average speed of the blood inside the aorta or blood vessel.